Today in CHEM100, we're going to finish up our review for the final exam. And last Tuesday, we made it up to number 71. So that's where we're going to pick it up today. And the video for part one is already posted and available. And this one will be posted within within 24 hours. So let's pick it up with 71. Convert 0.205 moles calcium hydroxide into grams of calcium hydroxide. This is a unit conversion. Very simplest technique that you need to know. If we want to end up with grams as our answer, then it has to be in the numerator. And we want to cancel that, which is in the numerator now. But when we multiply it by moles in the denominator, it'll cancel. So what that gives us is a hint as to what the conversion factor needs to be. Grams per mole, which is molar mass. So we need to calculate the molar mass of calcium hydroxide. Fortunately, for you, the formula is given. Right, so we need 1 calcium, which is 4008. And this is in grams per mole for that much in this molecule. Then we have 2 oxygens and 2 hydrogens. We just do the math now. And this is 74.10. So that's 74.10 grams for each mole. And that times 0.205, my calculator says 1.51905. Right? How many of those can we keep? We have 3 significant figures here. Conversion factors are exact numbers. They don't limit the outcome at all. So 3 significant figures there. We need to cut it off here. That means 1.52 grams. Oops. Decimal place. My mistake. 15.2. Pay attention. If you have your calculator set up for scientific notation, be sure to pay attention to the exponents. That didn't make any sense anyway, right? A tenth of 74 is about 37. But we're dividing it by twice as much, so half of 37 is around 15. That estimation tells me that I should not have made that mistake. Next, we'll skip a few repetitive ones, come down to 78. Ten moles of calcium metal is reacted with 3.9 moles of oxygen gas. How much calcium oxide is produced? And notice in the answers, we have moles. So we only have to determine how many moles of calcium oxide are produced. We're told that calcium metal, that's solid, is reacted with oxygen gas. Now, is that right? No. Oxygen gas is diatomic. If you don't know that, then you're going to get this problem wrong. Like that. Then you have to know how to write calcium oxide as a product. -2 + 2 We only need one of each. Okay. Now we need to balance the equation. We need 2 oxygens on that side. That means 2 calciums on this side. And that equation now is balanced. Once the equation is balanced, then you can go to solve the problem. 10 moles of calcium metal is reacted with 3.9 moles of oxygen gas. Right? Whenever you have explicit amounts of reactants, you can assume that one of them is going to be limiting. One will run out. We have to determine which one is limiting. So, if we have, let's see, we want to know how much calcium oxide. Okay, so let's do it this way. Let's take this 10 moles and say how much calcium oxide will that produce? Right, the conversion factor is derived from the coefficients of the balanced equation. So calcium cancels and leaves us with calcium oxide. How many moles of calcium? 2. How many calcium oxide? 2. So that means if we use up all of this calcium to produce calcium oxide, we'll get 10 moles of calcium oxide. Do the same thing with oxygen. This is O2. O2 here, calcium oxide there. The ratio then is 2 here and 1 there. So that's 7.8 moles of calcium oxide. All right, now we can tell instantly which one is limiting. This one produces the least amount, which means this is limiting. And by doing it this way, we have the answer. 7.8 moles of calcium oxide will be produced. That means oxygen is limiting. Calcium is excess. Okay? '81. For the reaction. And we're given the balanced equation. Isn't that nice of them? 2 sulfurs plus 3 oxygen yields 2 sulfur trioxide. Okay, now what are we going to do with it? How many moles of sulfur trioxide can be produced from 7.2 grams of oxygen and excess sulfur? So we're told this is excess already. That means whatever we're given for oxygen, 7.2 grams, will be completely consumed to produce sulfur trioxide. Okay? The problem with this is you can't move anywhere in a balanced equation with mass. You must have moles. There we go. Grams per mole. So what's the molar mass of oxygen? Well, it's 2 times 16, which is 32. There we go. So that tells us how many moles of oxygen, which is 0.225. I'm going to keep an extra significant figure here to avoid rounding error. We'll round the errors off at the end. right, with 7.2. Yeah, two significant figures, but I'm going to keep those. This is moles of oxygen. Now we need to convert to SO3. The ratio is 3 to 2. Okay. And that is 0.15000. Okay. So this is the number of moles of SO3. Does that answer the question? Yeah. Only we want to preserve the number of significant figures, restrict them to 2. So those go out and we're left with 0.15 moles of sulfur trioxide. $82. Okay. Consider the following unbalanced equation. All right. Aluminum carbide plus water yields aluminum hydroxide plus methane. All right. Is that reasonable? Well, only if you assume carbon is a -4 charge. So if this is -4, we know aluminum's +3. That's correct. Water's correct. Aluminum +3. Hydroxyl is a polyatomic ion with a -1 charge, so it takes 3 of them. And then methane is written correctly. We need to balance this equation. Now you have 2 options. If you're proficient at balancing equations, you might be able to do it just like that. Just work with that, what you've got. But if you're not, and if you want to practice, then use the budget method. All right. So we do an original tally, and a beginning tally: 4 aluminums, 3 carbons, 2 hydrogens, 1 oxygen. This side we have 1 aluminum, 1 carbon, hydrogens. 3 plus 4 is 7. And then oxygen is 3. Okay. All right. Now where do you start? Well, we don't have any single elements, so we can't hold those out. We generally hold water out if it's there till the end. So we could focus on just start at the top, start at aluminum. So if we do that, we need 4 here, which changes the oxygens to 3 times 4 is 12. Okay. And the hydrogens, 3 times 4 is 12. But 4 more, 16. 12 plus 3 is 16. All right. So now we can go to carbons. We need 3 carbons on that side. Now we have 12 here and 12 here. That's 24 carbon. It's 24 hydrogens, excuse me. 24 hydrogens. Okay. So that's balanced, that's balanced. Now what we need is to use water. If we need 24 hydrogens on this side and hydrogens are all in one place, then we can multiply by 12 and get 24 hydrogens. But that'll give us 12 oxygens. And there you go, we're balanced. Okay, once you have a balanced equation, then you can work with the rest of the problem. Okay. How many moles of water are needed to react with 206 grams of aluminum carbide? 206 grams, 206 grams, and we want to know the moles of water. Okay, so we need to convert this to moles, correct? That means grams on the bottom, moles on the top, and we need the molar mass of aluminum carbide. So what's aluminum? 2698. And carbon is 12.01. So let's see what that molar mass is for aluminum carbide. And I get 143.95. Divide that into 206, and we get 1.43105 moles. That's aluminum carbide. Now we need to convert that to moles of water. Okay. Conversion factors are derived from coefficients. 1 here, 12 there. 1 there, 12 there. Okay. So we multiply 12 times this value, and we get 17.17263 moles of water. But we started off with 3 significant figures. So we need to chop it there. That means 17.2 moles of water. Okay. That took a little extra work, but with practice and sticking to the method, you should have no problems. All right, next, 84. Consider the following reaction where X represents an unknown element. 6X plus 2B2O3 yields B4X3 plus 3XO2. All right, so this equation is balanced. We have 6X solid plus 2B2O3. And that's a solid. And that yields B4X3 solid plus 3XO2 gas. Okay, if 165 grams of X, 165 grams of X reacts completely with diboron trioxide, that's this one, to produce 2.29 moles of this one. Okay. What's the identity of X? Right? How do we determine the identity of any element? You have two choices. If you know the number of protons, the atomic number, it's easy and definitive. All right, there's only one possibility. If you don't have that information, then you go to molar mass. Molar mass is pretty good. There are places in the periodic table where the molar masses are close together for neighboring elements, but most of the time you can get the right answer and you don't need a tiebreaker. So we're stuck in this case with molar mass, right? I abbreviate that MW. Molar mass means grams per mole. Do we have the grams of X? Yeah, we already have the grams of X right there. 165 grams. We just need to know how many moles of X does that represent? Okay, so let's work with what we've got. If this is 2.29 moles of that product, can we use a conversion factor to find out how many moles of this one we have? And the answer to that is yes, we can. So if we have 2.29 moles of B4X3, then we need a conversion factor that will take B4X3 and make it into X. 6 here and 1 here. So 2.29 times 6 is 13.74 moles of X. That goes right here. And then we divide that into 165. And I get 12.00873 grams per mole. All right, we can only keep 3 significant figures. So if I do that, then we have 12 grams per mole. So you go to your periodic table and you look at the molar masses for the elements and you just follow along left to right, top to bottom, until you get to 12 grams per mole or close to it. And that turns out to be carbon. All right. Number 88. Consider the reaction. Magnesium silicide plus 4 water yields 2 magnesium hydroxide plus silicon tetrahydride. Okay. How many moles of the excess reactant are left over if we start with 39.1 grams of each reactant? Okay, so it's a little more complicated, but if we're methodical about it, we should be able to answer this one with that balanced equation. We don't have to do that. It's already balanced for us. Okay, and 4 waters. Oops. Let's try it again. There we go. Yields MgO2. MgOH2. And then there we go. All right. What are we given? 39.1 grams of each reactant. Okay. What we have to do is find out which one's excess and which one's limiting. We can't do that until we know moles. So we have to determine moles here first. right. We need the molar mass of magnesium silicide. Let's see. So we have 2431. 2 times 2431, and then 1 silicon, which is 2809. Let's see. Add those together. And I get 4, 8. Is that right? That doesn't sound right. Let me try that again. 2431, 2, and 28 point. That's better. 76, 71 grams per mole. 76, 71. That equals how many moles of magnesium silicide? 39.1. That divide 0.5097 moles. Okay, do the same thing for water. Okay, I'm going to move water down here so that we can work this one across and work water across. So water would be 39.1 grams of water. Moles, grams. We've done water so many times, I got it memorized. 18.02 grams. So we're going to divide 18.02 into 39.1. And I get 2.1698 moles of water. Okay. All right. How many moles of excess reactant are left? In this case, we're not interested in product because that's not what the answer we want. We want to determine which one of these is excess and then how much of it is left over. Right? So we need to convert this into moles of that and compare it to this value. All right. So our conversion factor is going to have water on the bottom and magnesium silicide on the top, right? Coefficient of 1, coefficient of 4. So I divide 4 into that one, and I get 0.54245 moles of magnesium silicide. Okay, so in order to use up all of this water, we need 0.54 moles of magnesium silicide. Do we have that much? No, we don't. So this one's going to run out. This one is limiting. This one is excess. All right. How much excess? Well, we subtract what we're going to use and see what's left over. All right. Subtract 0.5097. Moles. Okay. Now this is the equivalent moles of magnesium silicide that would be left over. But that doesn't answer the question, because now we need to convert that back to water. All right, now we have 4 here. We have 1 there. All right. Okay, so 4 times this value, 0.03375 here, 4 times, is 0.135 equals 0.135 moles of water excess. Okay? Or rounded off 0.13. That's the closest we can get. All right, that's one way to do it. The other way to do it would be to say, go the other direction. Right? Say, if we have this many moles of magnesium silicide, then how many moles? Convert this into moles of water, and we find out that that moles of water compared to this moles of water is too small, and subtract that from this one, and that would give us this value directly, which would be a quicker way to get there. But if we did that, we'd have to have some intuition about which one was limiting, and since I didn't, I just worked this way. Number 92. Okay, Fe3O4 reacts with carbon monoxide according to the equation. If 482.3 grams of carbon monoxide is reacted with excess Fe3O4, what mass of CO2 will be produced? This is even simpler than the previous problem. So, Fe3O4 plus carbon monoxide, or, yep, CO, yields, or carbon dioxide plus 3 iron. All right. This isn't required to solve the problem, but it's interesting to me. If this is an ionic compound and oxygen is a 2- charge, that means 8 minuses here. How do you get 8 minuses out of 3? Right? Well, 8 divided by 3 is, right, 2 2/3. Right? So 2 2/3 plus charge for the iron. All right, here's what happens. This is a valid expression for a compound, but it doesn't give you whole number charges. In order to get this one, you need FeO and Fe2O3. 4 oxygens, 3 irons. So that's probably the crystal structure of this compound. It has both Fe and Fe2O3. So we have 2 different charges for the irons. All right, now let's solve the problem. You didn't need to know that to solve the problem. 482.3 grams of carbon monoxide. Okay, that's what we're given, and excess compound here. All right, so we just need to convert this to moles and find out the mass of the CO2. Right? So we're going to convert that. Carbon monoxide would be 12.01 and 16. 2801. That cancels the grams, leaves us with moles. 482.3, 28.01, and I get 17.219 moles of carbon monoxide. Then we want to convert that to carbon dioxide. So the ratio is 4 to 4, right? So we got that many moles of carbon dioxide. Then we want to convert it back to grams, right? So we need the molar mass of carbon dioxide. Grams per mole. All right, so we still have one carbon, but now we have 2 oxygens. So that's just 16 more. 3401. And that's 58.56131 grams of CO2. And we started off with 4 significant figures, so we chop it off there. And that's 58.56 grams of CO2. Well, what did I do wrong? That was 585. But I did something wrong. Okay, let's see where I went wrong. Let's see. 482.3 grams of CO. Is this correct? I bet that's not correct. 28.01, is that right? Yeah, this is correct. So 482.3 divided by 28.01 is 17.219. Four 82.3 grams of carbon monoxide. Okay. Yeah. And that's this. That's correct. What's the question? What mass of CO2 will be produced? Okay. So this gives us the same moles of carbon dioxide. Is this correct? That's the question. All right, let's do it from scratch. CO2, 12.01 and 2 times 16. 4401. That's the problem. That was the problem. Okay, let's see, times. Now this is 757.8 grams of CO2. There we go. All right, 94. Let's see, 0.216 grams of sodium chloride dissolved in enough water to make 5.2 milliliters of solution. What's the molarity? All right, molarity equals moles per unit volume, right? This is moles, and this is liters. So if we've got 0.216 grams of sodium chloride, that needs to be converted to moles. And the author of the problem was kind enough to give us the molar mass of sodium chloride, 58.44. And I get 3.52 times 10 to the minus 3 moles of sodium chloride. Okay, that's this part. Now, how about the volume? In enough water to make 5.20 milliliters. 5.20 milliliters. Okay, correct units? No, needs to be liters. So the easiest way to convert, well, if you know 1,000 milliliters is in a liter, and we're going from small units to large units, that means the number has to get smaller. We go from small to big, big to small. That means we would have to move the decimal place to the left 3 places. Right? 1, 2, 3, right here. That would be liters. Okay, the other way to do it is to know what this means. Milli means 10 to the minus 3. So we're substituting this for that. 5.20 times 10 to the minus 3 liters. All right. So calculating the molarity, we have 3.52 times 10 to the minus 3 moles and 5.20 times 10 to the minus 3 liters. Okay. And I get 0.67788. And we only have 3 significant figures, so we're chopped off there. 0.678 molar. And well, what did I do wrong this time? Dissolved in enough water, 5.2 milliliters. 0.216. Let's see, my number is too small. So that means this one needs to be bigger or that one needs to be smaller. So let me check my calculations here. 0.216, 58.44. Yep. I don't know how it happened, but I got that one wrong. 70. So this is going to be 70. And that is 0.712 molar. Closest is A, 711. Don't ask me how that happened. I punched in the wrong numbers, probably. $95. Titration of sulfuric acid with sodium hydroxide. How many moles of sodium hydroxide would be required to react with 1.5 liters of 0.5 molar sulfuric acid to reach the endpoint? Okay. You have 2 possibilities here. If you calculate the normality of each solution, then you can use the normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. Right? That works. Or you can go to stoichiometry and write out the reaction equation. Sulfuric acid, sodium hydroxide, and you have to know what they make. they make a salt and water. So this would be sodium sulfate, which needs 2 there, plus water. That means we need 2 of those. That gives you the ratio of moles of sulfuric acid to moles of sodium hydroxide. Then you can plug in the values. Let's see, 1.5 liters of 0.5 molar. Right? So that would be 0.75 moles of H2SO4. Right? If I calculated correctly. And then you could convert to moles of sodium hydroxide. That's 1. This is 2. And that's 1.50 moles of sodium hydroxide that would be needed. Okay, that works. If we do it this way, what's the normality of sulfuric acid? If it's 0.5 molar in sulfuric acid, it is 1 normal in hydrogen ions. Because for every mole of this, you have 2 hydrogen ions. So the normality of the acid is 1 normal. And its volume is 1.5 liters. All right. What's the normality of the base? Oh, we don't know that. Okay, never mind. We can't use it. Right? We're not given the normality of the molarity of the base or the normality of the base, so we can't use that one. This is the only way to solve that problem. That means you've got to be able to balance that equation. You have to know that an acid plus a base makes the salt plus water. That's just a fact of nature. '96. Which of the following statements is false? Oxidation and reduction. Okay, we're looking for the false one. How about the first one? Cannot occur independently of each other. That is true. If you have an oxidation, you must have a reduction. This one's true. B, accompany all chemical changes. False. There are chemical reactions that do not transfer electrons. That's false. Right. Well, we have found the answer. C says describe the loss and the gain of electrons respectively. Oxidation, oil rig. Oxidation is loss. Reduction is gain. That's true. Result in a change in the oxidation states of the elements involved? Definitely. Always happens when an alkali metal and a halogen react. Yes, indeed, it does. Alkali metal and a halogen. Right? So if we do 2 there, we got 2 there. This one's 0, that one's 0. This one's +1, that's -1. It always happens that way. When you have elements on one side and compound on the other, you get a change in oxidation states. You have a redox reaction. All right, so the answer to this question is B. All right, 97. You have 3 liters of 3 molar solution of sodium chloride. Call it solution A. You also have 2 liters of 1.84 molar solution of silver nitrate, called solution B. You mix these solutions together, calculate the concentration of nitrate ions in solution C. All right, so we have sodium chloride reacting with silver nitrate. And that's going to produce silver chloride precipitate plus sodium nitrate. Okay. And that's balanced just the way it is. All right, we're given 3 liters of 3 molar sodium chloride. 3 liters of 3 molar sodium chloride. And then we're given 2 liters of 1.84 molar. 2 liters of 1.84 molar silver nitrate. Okay. What's the concentration of nitrate? All right. What you have to understand is that nitrate is a spectator. That means the number of moles you start with is the same number of moles you end with in solution. Right? So if we want to know the moles here, 2 times that is 3.68 moles of silver nitrate. But since this is in solution, it's also 3.68 moles of nitrate ions. Okay? You have that same number of moles when the reaction is complete. But what has changed? The volume has changed. Now we have this many moles to what volume? Well, we have 3 liters of this and 2 liters of that. So that's 5 liters. And that means 0.736 molar nitrate. Okay? We started out with 1.84 molar. We ended up with 0.736 molar. That's a simple case of dilution. All right. 99. Let's see, which statement is true of the following reaction? Let's see, we have 2 potassiums and copper 2 chloride yields 2 potassium chloride and a copper metal. Okay. This is a redox question. So which one is true of the following? E says 2 of the above. If we're looking for the true statement. Okay, so potassium is oxidized. Well, let's see. Potassium starts off with a 0 oxidation state, copper 0. Chloride is -1, so that's a +2. And this is -1, and this is a +1. Okay. If we go from potassium to there, we had to lose 1 electron. 1 electron for each potassium. Okay. Potassium is oxidized. It's a loss of electrons. Yes, it was oxidized. That's true. B says potassium is reduced. Can't have both. Not the same reaction. So that one's false. How about C? Copper is reduced. Copper goes from +2 to 0. How did it get there? It had to gain 2 electrons for each copper. Right? Reduction is gain. So yeah, copper is reduced. And again, it can't be oxidized and reduced at the same time, not in this reaction. Right? So 2 of the above is your answer. Let's see, 102. That was given out on me. 102. In which of the following does nitrogen have an oxidation state of +5? All right. A, B, C, D, and E. Give ourselves plenty of room. So we have HNO3. We have NO2. We have N2O. We have NH4Cl. And we have NaNO2. Okay, oxidation states. -2 here, +1 there. So we have a -6 and a +1, which gives us -5. That makes this one +5. There's our answer. We can do the rest of them if you wanted to. This is -2, so that's +4. -2, this would be a +1. This is a -1, +1, so that's a +5. +4, -1 is a +3, that's a -3. And this is a +1, -2, -4, -3, +3. There we go. Okay, so we found our answer. A is the answer for this one, but if for some reason it comes up with a different number, right? Say you're looking for +3, then you would go to this one. All right, 103. 103. Which of the following is true for a galvanic cell based on the following reaction? All right. So we have zinc, solid, plus copper 2 plus in aqueous solution yields zinc 2 plus in the aqueous solution and copper solid. Okay, if we're looking for reduction, oxidation, anode, cathode, we need to know what's going where. Right? So the zinc would go from here to here, and that would be a loss of 2 electrons per zinc. Copper going from here to here would gain 2 electrons per copper. Okay, so zinc is being oxidized. Right? So this is oxidized, which means what? In terms of a galvanic cell, the site of oxidation is the anode. This would be reduced. So the site of oxidation here would be the cathode. Reduction would be the cathode. Now we can answer the questions. All right, zinc is being, see, A, B, C, D, and E. Zinc is being reduced. No, zinc is oxidized. B, zinc serves as the cathode. No, it's being oxidized. It's the anode. Copper 2 plus is being reduced. Yes, it gains electrons. That's true. Copper serves as the anode. No, it serves as the cathode. And two of these are true. Well, no, only one of them is true. Only C is true. Now, if we were to set up this cell, if we were to make a galvanic cell, how would we arrange that? Well, we would have this solution and this solution. Which one would be the cathode? By default, the cathode is on the right. So this would have a copper electrode here. Right? We might send it through a meter. And here, and electrons would be moving this direction. And this would have our copper 2 plus ions in it. This one would have a zinc electrode in it. And this would have zinc 2 plus in solution. Okay, then we would have a salt bridge. Okay, so what does that mean? That means electrons are leaving here and zinc is becoming zinc 2 plus. Zinc is becoming zinc 2 plus. In this one, copper 2 plus is becoming copper metal, going from copper 2 plus to copper metal. Right? So in a balanced equation like this, the anode is one section, the cathode is another section, like that. 105. The total mass of a solution is 184.8 grams. The solvent mass is 125.2 grams. What's the mass percent of the solute? Okay. Let's see. What is the solute? The solvent mass is 125.2 grams. Solvent. 125, right? Yeah, 0.2 grams. Right. The total mass is 184.8. Total 184.8 grams. Right. So what's the mass of the solute? It's just the difference. There we go. So the mass percent equals 59.6 divided by the total times 100. So that's about 3. No, 32, excuse me. Let's stop trying to use my brain and use my calculator. Yeah, 32, 32.3% by mass. Okay. $106. Which of the following statements is true of electrolysis? Okay. Remember what electrolysis is. It's just the reverse of the galvanic cell. We're driving the reaction backwards. So electrolysis is a process where electrical energy is used to produce a chemical change. Yeah, that's true. Electrolysis involves forcing a current through a cell to produce a change that would otherwise not occur. That's right. The galvanic cell is spontaneous. The electrolytic cell is not spontaneous. We have to force it in the reverse direction. That's also true. C, the electrolysis of water produces hydrogen gas and oxygen gas. Yes. Hydrogen and oxygen react, whether it's in a rocket engine or it's in a fuel cell, it produces water. If we reverse that reaction, we produce hydrogen gas and oxygen gas. That's true. Electrolysis is used to recharge a lead storage battery. Exactly correct. We use power from the battery to start the engine. That's the galvanic cell. Then the alternator is spinning under the connected to the engine, and it reverses the charge through the battery and recharges it, which is an electrolytic cell. We drive the reaction in reverse. So that's also true. That means all of those are true. 107. Let's see, the oxidation state of chlorine in ClO3 minus. ClO3 minus. All right. Oxygen is -2 times 3 is -6. We hold one negative out for that one, which means chlorine is +5. Okay. 108. The oxidation state of oxygen in O2. Right. All elements in their most stable form at room temperature and 1 atmosphere pressure is 0. 109. Let's see, the oxidation state of sulfur in K2SO4. Right? We have -2 here, that's -8. And potassium is an alkali metal, so it's a +1, +2. So these together, -6. That means sulfur is a +6. (110). When the following reaction is balanced in acidic solution, the coefficient of water is. All right. So we need we're going to use the half reaction method to balance this equation. ClO3 minus, this is what's given to us. Fe2 plus, Cl minus, and Fe3 plus. All right. Those are participants in the reaction. Any other omitted ions are spectators. So there would be a cation associated with this one, an anion associated with that one. And they'd still be here on both sides. So we just throw them out. We don't need them. Not to balance this equation. All right, half reaction. Oxidation step and reduction step. So we need to know which one's which. Well, these are 2 plus, minus, and 3 plus. We just need to know what these are. What is chlorine, right? -2, -6 total, -5 because we hold 1 out for that. This is a plus 5. Now we can move. So which one is oxidized? Which one loses electrons? Iron. It loses 1 electron for each iron. So Fe2 plus goes to Fe3 plus. That means ClO3 minus goes to Cl minus. Okay? Next, balance the non-oxygen, non-hydrogen atoms. That one's good. That one's good. Now we balance the oxygens. This one doesn't need it. That one does. It needs 3 oxygens on this side. And we do that as water. But that puts 6 extra hydrogens over there. So we need 6 hydrogens on this side. Okay? And this is in acidic solution. So once we get this balanced, we're done. We don't have to change it to basic. It just stays the way it is. All right. Now we do electrons. This is oxidation. That means we have 1 electron on that side, right? In oxidation, electrons are represented as a product. They're reactant for reduction. So how do we get to plus 5 to minus 1? We add 6 electrons. 6 negatives plus a plus 5 is a negative 1. That's what we have right here. Now we need to balance the electrons. Well, if we multiply this one times 6, then that'll do 6, 6, and 6. Okay. Okay, we only have waters here. So when we bring them down, we're only going to have waters on that side, which means we don't have to finish this out. The answer to the question, what's the coefficient of water? It's 3. All right. Let's see, 111. The Hall process for making aluminum involves what? Chemically reacting aluminum with carbon? No, this is not. This is an electrolytic process. Right? We're taking aluminum in aluminum oxide and we're reducing it to aluminum metal. So electrolysis is the only one that works here. So B or C is possibility. Electrolysis of an aqueous solution? No. If we drive that much current through an aqueous solution, all we're going to get is hydrogen and oxygen. So it must be a molten solution of aluminum oxide, and those should have subscripts. My mistake. Aluminum oxide and sodium aluminum fluoride. That's added. That sodium compound is added to reduce the melting point of the aluminum oxide. We have to get it we have to melt it in order to free up the ions, right? If we don't free up the ions, then we can't drive current through it, right? It'll just be an insulator. We need a conductor. So C is the correct answer here. It's electrolysis of that molten solution. 112. Okay, how many electrons are transferred in the balanced reaction? Okay. 2 ClO3 minus. Right? We are told that this is a balanced equation. So we don't have to go through the half reaction procedure. We just have to assess the electron movement. Okay, so what's what? Well, the oxidation state there is 0 and 0. There's a -1. This is chlorine is a +5. We did that one earlier. Okay, so we're going from +5 to 0. Right? That's a gain of hold on a second, let me check this out. -2, -6, yeah, that's +5. Okay. +5 to 0. So it's a gain of 5 electrons per chlorine times 2 chlorines equals 10 electrons. So if this is balanced, then the oxidation step should go from here to here. A gain of 1 electron per iodine times 10 equals 10 electrons. So 10 moles of electrons are transferred in this process. That's E. All right. Let's see, number 113, right? Yeah, 113. Okay, when the equation for the following reaction is in basic solution is balanced, what's the coefficient of hydroxide? All right, if it's in basic solution, we should have some hydroxide in there somewhere. So let's do our fake acid method. MnO4 minus. And I'm going to leave out the, yeah, I'm going to save room and leave out the phases. Here we go. Okay, oxidation states. In order to calculate the oxidation state of carbon, we need to know a nitrogen. So nitrogen, we're gonna call it a -3. That means -2 is only needed here. So +2 here. Okay, let's do the same thing over here. -2 and -3 yields -5, but we can hold one out for that. -4, this is +4. Remember, this is just a bookkeeping scheme, right? We're not saying that these atoms are charged. They might be, but they don't have to be. Not for our bookkeeping scheme. Manganese here would be +4 because that's a -4. And here would be -2 times 4 is -8, -7. So that's +7. Okay, now we can assess oxidation and reduction steps. Okay, which one is oxidized? Carbon goes from +2 to +4. That means it's oxidized. Okay, that means manganate ion +7 for manganese goes to manganese dioxide. Manganese 4 dioxide, actually. Okay, now let's balance the rest of them. Well, 1 carbon, 1 nitrogen on both sides, we're good. Manganese on both sides, we're good. So now we're going to balance the oxygens. This means 1 oxygen there and 2 hydrogens on that side. This needs 2 more oxygens on this side, which means 4 hydrogens on this side. Okay. Now electrons. We have, how do we get from +2 to +4? We have to lose 2 electrons. And since there's only 1 carbon each, that's all we lost. In this one, we have 1 manganese and 1 manganese. This one had to gain +3 electrons. Right? 3 negatives, so +7 yields +4. All right. How do we reconcile 3 and 2? We multiply this one times 3, and this one times 2. Okay, so this is 3, 6, 6, and 3. And this one is 2, 8, 6, 2, and 4. Okay, so now we can bring everything down. So I'm going to bring this one down first. 2MnO4 minus, and then Cn minus. I'm sorry. 3Cn. 3Cn minus. That one. 3 waters. Right? And 8 hydrogens. And the electrons are canceled out. On this side, we have MnO2. 2 MnO2. And then we have 3 CnO minus. All right. 2 MnO2. CnO, that's right. And then next we put water. So we have 4 waters. And do we have any hydrogens? Yeah, we have 6 hydrogens. 6 hydrogens. Okay. Let's cancel and consolidate. 3 water on this side, 4 on that side. So those waters go out, and we're left with 1. Hydrogens, we have 6 on that side, 8 on this side, so that means 2. Okay? So now we want to make it basic. So we add 2 hydroxyls to both sides. Okay? That makes 2 waters on this side. Okay? And that water on that side goes out, and now we're down to 1. Okay? But we have 2 hydroxyls on that side. Right? So that's the answer to that is 2. 2 hydroxyls when we're balanced in basic solution. Let's see. Okay. 1:15. Yeah, we got time, I think. Oops. 15. This one's about to give out. Write the balanced equation for the double replacement reaction of lead-2 nitrate, potassium chromate. Okay. Lead-2 nitrate. Lead has a 2+ charge, with nitrate, which has 1 plus charge, so we need 2 of these. Okay, and this is aqueous solution. Okay, with potassium chromate and CrO4, which is a 2 minus. This is 2 minus polyatomic ion plus 1, so we need 2 of those. Okay, so the double displacement reaction says that this potassium takes the place of that lead. So this would be potassium nitrate, 1 plus, 1 minus, still an aqueous solution, and then lead chromate, which is a solid, right? It precipitates. Okay, now we want to balance the equation, right? The nice thing about these double displacement reactions is that they very well behaved. In other words, we can balance this just by looking at it. We've got 1 lead here, 1 lead there, 2 nitrates. We need 2 nitrates. That gives us 2 potassiums, 1 chromate, and that's balanced. 1, 1, 2, and 1 are the coefficients. All right, so there you go. Now, the problem with what I presented here as an answer is I'm not using subscripts, and I should be using subscripts. All right, let's see. There are a bunch of others that you can practice with. How about 124? Okay, aluminum oxide reacts with carbon monoxide. Aluminum oxide, solid, plus carbon monoxide, gas. And this is going to be -2 plus 3. So we need a 3 over here and a 2 over there. Okay. Does it tell us the products? Aluminum metal and carbon dioxide. And we want to balance that. Okay. Let's use the budget method here. Just in case. Oh, and carbon. Okay. 2 aluminums, 1, 2, 3, 4 oxygens, and 1 carbon. On this side, we have 1 aluminum, we have 2 oxygens, and we have 1 carbon. Okay, we're going to try to hold aluminum out till last. Oxygens. All right. Yeah, let's focus on the oxygens. If we put a 2 here in front of that one, right? That'll give us 4 oxygens, but it'll change the carbons also. It changes the carbons to 2. Oh. All right, we're going to have to go around the barn a couple of times for this one. If we put a 2 here to fix the carbons, now that changes the oxygens to 5. Right? Yeah, that changes the oxygens to 5. All right. What we need now is to reconcile, right? If we put a 2 here, that takes care of the aluminums. That's not a problem. But if we're going to reconcile this 5 and that 4, notice that these oxygens are in two different places. If we make this one even, how do you make this one even? Well, you either got to put a 2 in front of this one or a 3 in front of that one. If we put a 3 in front of that one, that makes 3 plus 3 is 6, right? That makes 6. Now we can put a 3 in front of this one, and that makes 6. Okay? It takes practice. I'll grant you that. You might struggle with something like this for a while, but the only answer is practice. Work as many of these balancing examples as possible in order to get experience in learning these tricks. All right, that's it. All right, so we've finished our review. All the highlighted ones that I wanted to be sure you got a chance to review. That doesn't mean you skip the others. It just gives you an idea of the type of questions that you will see on the final. All right. So we're done for today. We're done a little bit early, but our exam will be in Brightspace, right? And it should be open now, actually. I wouldn't advise taking it yet. You need to study a little bit, but when you get ready, the exam is in Brightspace and available for you to take the exam.